Section 6.2 is about compound interest. I want to compare compound interest to what we've done with simple interest, so a quick review. $50,000 invested at 9% nuts per year for 3 years with simple interest. I get 9% in the first year, which is $4,500 of interest. And then I get the same interest, 9% on the same $50,000. I get another $4,500 in year 2. And in the third year, another $4,500 for a total of $63,500. To discuss compound interest, we're going to take the same $50,000. We're going to invest it at 9%, but now we're going to allow the 9% to compound annually. So here's how it works. The first year, nothing looks much different. You get 9% interest, which is $4,500. But at the end of the year, that $4,500 gets added into the balance. And from here on out, you'll be earning interest on $54,500 instead of the original $50,000. So this interest gets to earn its own interest. So when we go into the second year, we're going to have 9% interest on $54,500. Now we're going to make $4,905 of interest. And compared to what I got in the first year, I get another $405 of interest because last year's interest is allowed to earn interest. So I add this onto the balance from the end of year 1, and now I have $59,405. And then during the third year, the original $50,000 gets to earn interest, $4,500 from the first year gets to earn interest, and $4,905 from the second year all gets to earn interest. So I have 9% of $59,405. That third year's interest amount is $5,346.45 for a grand total $64,751.45. So you can see how compared to simple interest, compounding is a lot better to let your interest earn interest. I'm going to go back and do this again, but a little bit faster. After the end of the first year, I will have my original 100% of my $50,000, plus I'll have 9% interest. So I will have 109% of my original principal. I can do that in one calculation by multiplying by 1.09. So if you take $50,000, multiply it by 109%, you will get immediately to the $54,500 number. So each time the money moves forward, you multiply it by 1.09 for 109% of your money. Well, then from year 1 to year 2, if I multiply by another 1.09, 1.09 this time times the $54,500 number, I get directly to the $59,405. And then multiply by 1.09 again, I will get to my total of $64,000. So instead of stopping and adding up the individual interest all along the way, I can kind of do it all at once. Now I'm going to make it even faster. I start with $50,000. To move it to the first year, I times by 1.09. And without stopping to calculate this, I'm going to move from the first year to the second year, multiply by another 1.09. From the second year to the third year, multiply by another 1.09. In math notation, that would be 50,000, 1.09 cubed. So for 3 years, or 3 times, 3 arrows moving the money forward, 50,000, that will give me the same $64,751.45. So from this, we learned that compounding is good. So I'm going to compound more often. I'm going to take the same $50,000 investment and the same 9% per year, but now I'm going to compound semi-annually, so every 6 months. So I'm not going to have an arrow that goes, I'm not going to push the money clear till the end of the year. I'm going to stop after 6 months and figure out my interest, and then I'll move it forward for another 6 months. Okay, so the 9% was for the whole year. Well, then now that has to be divided into 2 equal pieces. So it'll be 4.5% for the first 6 months and 4.5% for the next 6 months. So each one of these arrows needs to be 104.5% of the original investment. So I take the 100% of my principal and I add on another 4.5%. So each arrow will multiply by 1.045. Multiply again by 1.045. So each time I advance the money 6 months, I multiply by 1.045. So when you compound more often than once a year, you need to figure out your interest per period, which will be your annual interest rate, and then divided by the number of times you compound within a single year, which in this case was twice. That gives me the 0.045. And then the total number of periods will be 3 years times 2 times per year, which would be 6. So I'll take my original principal, and each arrow that advances the money is 1.045 for an interest factor. And I will have 6 of those, 6 periods throughout the course of that 3-year investment. That gives me a total $65,113.01. So you can see that compounding just gets better and better the more often I do it. However, there's kind of a law of diminishing returns. So let's do this one more time, and then we'll go to Excel. What if you compounded every day? I need to know the interest per period and the total number of periods. Interest per period will be 9%, that's for a whole year, but now you have to divide it into daily pieces, so that would be divided into 365 compoundings per year. Each day's interest rate is 0.000246575, and there are more decimal places, so either store this or use 0.09 over 365, but don't round it off or else your answer is going to come out wrong. Those decimal places all end up mattering a lot. The total number of periods would be 3 years times 365 days per year. That's 1,095 times. So now if I'm picturing a number line, here's 0 and here's the end of year 1, you've now got a whole bunch of teeny tiny little arrows just advancing the money one day at a time at a little fraction of an interest rate, and you're doing this 365 times each year for 3 years. I can get to my total pretty quickly by starting with my original principal and multiplying it by 1 for 100%, plus my daily interest factor is 9% divided by 365. This is plus the 0.0246% more. And then I have to do that for the total number of periods in all 3 years, which is 1,095. I got $65,496.04. So even though I went from 2 times a year to 360 times a year, I've only gone up about $380 over the total over all those years. And even if I went to like compounding it every second, it doesn't get a whole lot bigger than this. In fact, in mathematics, there's something called compounding continuously. And when you compound continuously, you don't talk about how many arrows there are. Now there's like an infinite number of little arrows, and you get just this little tiny fraction of interest rate. Your formula totally changes, where your future value is your principal times the magic number E, it's called the natural number E, raised to the annual interest rate times by T. So this is for infinity compoundings per year. And all of our formulas break down when we try to plug an infinity in to the formula, and that's where this E comes into play. So here's how it works for continuously compounded. You take your principal, 50,000, times E, and there is an E key on your calculator somewhere by the LNX key, or your LN key. You should have a key that says EX. So be E raised to the, take the full annual interest rate of 9%, multiply up in the exponent by the number of years. In this case, 50,000 E to the 0.27 is what the exponent will simplify to become. which will give you $65,498.22. And that's if you compound every second, every fraction of a second, every moment. In the course of 3 years, you only get $2 more than if you only compounded daily. But this formula, called the PERT formula for obvious reasons, it applies for compounding continuously, and that means you have lots and lots and lots of compound periods every year. I'm going to teach you how to use Excel to do these problems, and then Excel can be your calculator. Excel uses several variables, and we just need to understand where they fall on the number line. So at time 0 is PV, which is your present value. And then wherever you end, the amount of money at that point is your future value on the last day of the investment. And then you have the option, which will come up in sections 6.3, 6.4, and 6.5, that you could make payments along the way at regular intervals, regular size. And for our purposes in this class, your last payment will always fall on the same day that you want to add up your future value. So we call this the end of the period, that the payment doesn't start at time 0, it comes at the end of the period. Those payments can add on to your investment, in which case they're deposits, or you could take away from the amount that you have in the bank. They could be withdrawals. So your payment could be either a positive number or a negative number. In section 6.2, the payment is always 0. We're not adding in any extra deposits or taking out any withdrawals. But that will come into play in 6.3 and 6.4. Then we have an N per, which is the total number of periods, which is the same as saying the total number of payments that are made. So how many of these extra payments did we have, or how many arrows did we have advancing the money? And then lastly, this one's so important, it's getting done in red. It's an interest rate, but this is the interest per period. So if it's compounded, you have to divide your annual interest rate by however many compoundings per year. So I like to put in an extra variable, which I just call the compoundings. So it's the number of periods in 1 year. Okay, let's pull up Excel and put Excel to work. I'm going to want the future value, which is FV. I want the present value, PV. I want the annual rate. I want the number of years of the investment. Those are the, and the payment amount, if any. So again, in this section, we're not going to be adding or subtracting anything from our original principal, so our payment will be 0. Then we're going to calculate the number of periods, which is called N per, and then we're going to find the rate per period. To redo our example, we're trying to find the future value, so that will stay blank. The present value will be 50,000. The annual rate was 9%. The number of years of the investment was for 3 years, and the payment was $0. Okay, now the total number of periods needs to be calculated. That will be once per year. I need to go back and add in a variable for the number of compoundings. Since this is annual compoundings, I'll have once per year. Then my total number of periods will be 3 years times by 1 time a year for a total number of 3. So 3 arrows advancing your money forward. Your rate per period is your annual rate divided into, well, just once per year. So that should still be 9%. Okay, now for the future value, I can calculate it. Excel has some formulas built in, and the formula for future value is called FV. Notice that it comes up, there's one that's FV and one that's FV schedule. We use the regular FV, and to select that, you can hit the tab button. And then notice that when I hit the tab, it put a parenthesis in here. And then I also have like a template for what information Excel needs in order to figure out the end value of this investment. First thing it wants is the rate. That is a rate per period. It's not the annual rate, it's per period. Number of periods was 3. Then it wants the payment, which is nothing, no additional deposits or withdrawals. Present value was 50,000. And then type is either at the end of the period or at the beginning of the period. I will leave the discussion of the difference of this to your Finance 3100 teacher. For our purposes in this course, all we ever do is end of the period. That's what Excel will default to. If you want to select it, you can type a 0 to select this option. And now when you hit enter, it says $64,751.45, which is what I got when I did the analysis before. Let's try it again. Let's do that same problem, the same $50,000 example that we started with. Future value, I'm still trying to find. Present value is still 50,000, annual rate 9%. But now the compoundings, compounded semi-annually, that will be 2 compoundings every year. Number of years is 3, payment. Okay, now for the total periods, I would need to have 3 years times by 2 compoundings each year for a total of 6. So compoundings per year times number of years. Rate per period will be my annual rate, but now it needs to get divided into however many compoundings you have each year, that many equal pieces. So 0.09 divided into 2 equal pieces, there's the 4.5%. Then my future value will be FV, tab to get that formula active. Notice it puts the parenthesis in for me. First thing it wants is the rate. That's the rate per period. Separate with a comma. Total number of periods is 6. Payment amount, no additional deposits or withdrawals. Present value, 50,000. And the type, you can either put a 0 or you can just leave it blank and Excel will assume it's a 0. So at this point I can just say enter. 65,113 and 1 penny. There it is, 65,113 and a penny. For compounding daily, now that I have everything set up, if I just change the compoundings to 365 compoundings per year, these other 2 cells were built on that cell, so it should automatically update my total periods and my rate, which it did. There's the 1,095 and my interest rate, which looks like it's rounded, but it's not. Excel is going to keep all of those digits in there. And it updated my future value also. There it is, 65,496.04. For compounding continuously, mathematically you would change to an E. You can get around that by just saying you're going to compound a lot. So just change the 365 to like instantaneous compounding. I'm going to put 500,000 compounds in there and then see what happens to the total number of periods. Rate per period went to scientific notation. There it is. And then here's my total value of the account, 65,498.22. There it is. Okay, let's go to WebAssign. Okay, the first problem just wants me to identify some variables. So I'm taking 9% is going to compound monthly for 7 years. So for the annual interest rate, and as a percent, that would be 9%. Length of the investment in years is 7. The periodic interest rate, so that's the interest per period. I will need to take the annual rate of 9% and divide it by the number of periods, and that was monthly compounding. So divide by 12 will give me 0.0075. As a decimal, to make it a percent, you move the decimal 2 places. So it would be 0.75%, and that's a per month. Total number of periods of the investment, well, 7 years of monthly compounding. So the total number of periods will be 7 years times 12 months per year would be 84 months of compounding. Okay, let's look at question number 2. What is the future value if $9,000, that's my present value, is invested for 8 years, 10%, and then semi-annual compounding? I'm trying to find the future value, so that will stay blank. The present value will be 9,000. The annual rate is 10%. Compoundings that's per year, and this was semi-annually, so that would be 2 per year. Number of years was 8. Payment will be 0 in section 6.2. Total number of periods will be 8 years times 2 compoundings per year for a total of 16 different compounding periods. The rate per period is the annual rate of 10%, but then it has to be divided into 2 equal pieces. So 5% every 6 months for a total of 10% over the course of a year. Future value, pull up the FV formula. I need the rate, which is the rate per period. Number of periods, 16. Comma, payment 0, present value $9,000. The type, you can either just leave it blank and Excel will default to a 0, or you can take control of your life and put the 0 in there. 19,645.87. Don't worry about the fact that you have parentheses around it and that Excel thinks it's negative. We will deal with that in the next section. 19,645.87. Number 5, what present value? So we're looking for the present value amounts to 25,000. So that's after the investment is done. That's the future value. What present value amounts to 25,000, 10 years, 7% annual compounding? All right. My future value is now known. That's going to be 25,000. Present value is what I'm looking for. Annual rate was 7%. Yes. Compoundings once per year, annual compounding for 10 years, no additional payments or withdrawals. Total number of periods will be 10 years of 1 per year. Rate per period will be 7% divided into 1 per year. And then to find the present value, I don't want to use the FV formula because I already know the future value is 25,000. I wonder what the formula in Excel for the present value would be called. Well, you're right. It is PV, but I need an equal sign to call it up. Equals PV. There it is. Returns the present value of an investment. That's the one I want. Rate per period, 7%. Okay, now I could, just for the record, I could type that in. But once you've got this all built, it's so much easier just to point and click. So rate 7%, number of periods is 10, payment, nothing extra, future value 25,000, type, have it default to a 0. Oh, I gave it 70% interest. Huh, no wonder. That's why you don't type it. You should really just click it. Okay, let's try that again. $12,708. That sounds better. So if I take $12,708.73 and I invest it for 10 years at 7% and it compounds once a year, At the end of those 10 years, I will have $25,000. Let's look at number 8. Number 8 is going to compare interest rates. So in this case, life insurance policies that are paying interest, and you want to know which is better, 4.5% that compounds monthly versus 4.52, a little bit bigger interest rate, but it compounds less often. So smaller interest rate, more compounding, or a bigger interest rate, less compounding. To figure that out, we're going to find the effective rate of interest. And I think the easiest way to think of the effective rate of interest is you're going to look for the interest on $1 for 1 year. So the present value will be $1 and the years will be 1. So let's find the effective rate for 4.5% compounded monthly. I want to find the future value on a present value of $1 at 0.045 per year, but compounded 12 times monthly. I only want to go for 1 year, no extra payments. My total number of periods matches 1 year's worth of compoundings because I go for 1 year. And then my rate per period would be 4.5% divided into 12 equal pieces. I want to find the future value formula. And I need the rate, comma, number of periods, comma, payment of 0, present value of $1. Let it default to end of the period payments. And you get 1.05. I need to see more decimal places than that. So we're going to format this cell. Let's open up the home page. And right now, that formatting is in currency because it's got a $sign on it. Here, I don't want currency. I want to go to number. And on the number, I want to go to number, and then these tabs will move the decimal either to the left or to the right. I want to move the decimal. I want to see more decimal places. There we go. And again, ignore the negative for now. In the next section, I'll tell you why it's doing that. My $1 grew to $1 and 0.4594. Read this like a percent. I now have 104.594% of my money. So I want the interest only, so take off this original dollar. My money grew by 4 cents and a little bit. Make this into a percent by moving the decimal 2 places. That number is read as 4.594%. And then they want me to round to 3 decimal places. There it is, 594. Okay. 4.594%. Let's compare that to 4.52% if it's compounded semi-annually. So I'm going to go back. I still take $1, but now my annual rate is 0.04%, 4, and then a 5.2. Compounding only twice per year, still for 1 year, so an effective rate $1 for 1 year. Total number of periods is now 2, and it took my interest rate and cut it into 2 equal pieces. There's my effective rate. 1.04571. I want the interest only, so take off the dollar and then move the decimal 2 places. That's 4.571. So in this case, the monthly compounding was enough to make a lower interest rate yield more, because the lower rate will turn into 4.594. This is only 4.571. It's a good way to be able to compare different interest rates. Let's look at the Microsoft problem. 13 years after the initial public offering of a stock. So Microsoft has an incredible history in the stock market. Let's take $50,000 invested on day one at the initial public offering price, and it grows to $3 million after 13 years. Okay, let's put this in there. Future value is $3 million. This is the first time I've had to do a present value and a future value. So now I need to just tell you that one of those has to be negative. You have to think of either the future value or the present value has to be negative. I'll put it on the present value. Annual rate is what we're trying to find. Compoundings, compounded annually, so that'll be 1. Years was 13, and no additional payments. Okay, the total number of periods will also be 13 because it's only once per year, and the rate per period is what we're trying to find. Okay, for the annual rate, Excel has a formula for that, and they call it rate. Now there's a lot of different rates in here if you look. I want the just plain RATE rate, returns the interest rate per period of a loan or an investment. I need to tell it the number of periods, 13. That was once a year for 13 years. The payment, no additional payments. Present value, a negative 50,000. Future value, a positive 3 million. Those just have to have different signs. And then the type, default to 0 for end of the payment. And then a guess, you don't have to put in a guess. It helps Excel do the numerical calculations, but you can ignore the type and the guess. Interest rate, 37%. Round your answer to 2 decimal places. Okay, so let me highlight this cell and then go to the Home tab and the number, and I want to see more decimal places. So 37.02%. Let's do number 11. I'm going to do it 2 ways, one by hand and one on Excel. A machine is valued at $10,000. That's its value right now. So it'd be like a present value. If the depreciation at the end of each year is 30% of its value, so it loses 30% every year, find the value at the end of 4 years. So my mind sees this. In the first year, it's going to lose 30%. So that means its value will be 100% of the beginning value, but take away 30%. If it loses 30%, it's going to keep 70%. So you're going to times this by 0.7, and after 1 year, its value will only be $7,000. And then for the next year, that number, that 7,000 is going to lose 30% more. So if it loses 30%, it keeps 70%. And now it will only be worth 4,900. I can make this go faster if I just start with the $10,000 and I think of 100% minus 30% every year for 4 years. That would be 10,000 times 70%, make it a decimal, to the 4th. After 4 years of that depreciation, your final value will only be $2,401. Okay, how would we do that in Excel? Well, I'm glad you asked. We're trying to find the future value. The present value is 10,000. The annual rate, okay, this is a rate of interest. So Excel expects a positive number, but if it's declining, I'm going to put in a negative 30%, so it's losing 30% of its money. Compoundings is at the end of each year, so every year it loses 30% from the previous year for 4 years, and no additional devaluation going on. Total number of periods, 4, the same as the years, and the rate per period, losing 30%. Future value equals, to put it into calculation mode, future value with a tab, interest rate per period, lose 30%, comma, for 4 years, no additional payment, start out with a value of 10,000. You can have it default to 0 for the type. And there it is, 2401. And notice that Excel puts opposite values on the future value and the present value. And I will explain that in the next section, something to look forward to. Okay, between this and the videos, you should be good. So have a great day, and I will see you in class.